And I'd like to introduce Paula Crowley, who will introduce our program and our presenter for today. Thank you.
Okay, well, thank you, Julianne, and welcome everyone to the third talk in our series on artificial intelligence. Today's speaker is Dr. David Vaillancourt, who is currently professor and chair in the Department of Applied Kinesiology and Physiology. And his research focuses on how the brain regulates movement with a specific focus on voluntary and involuntary motor disorders. Dr. Vaillancourt received his Ph.D. and master's degrees from Penn State University in motor control and gerontology, and a bachelor's degree in kinesiology and mathematics from Texas A&M University. His research program at UF uses advanced neuroimaging techniques to study the functional and structural changes in the brains of people with motor and cognitive disorders that span Parkinson's disease, tremor, dystonia, and Alzheimer's disease. Dr. Vaillancourt has conducted studies investigating interventions, including rehabilitative, surgical, and pharmacological interventions. And he has authored or co-authored over 150 papers in journals that include Brain, Journal of Neuroscience, and Lancet. He's been continuously funded by the NIH since 1999 and is currently funded for several R01 and U01 grants from the NIH. He has served as chair of the NIH study section, Motor Function, Speech, and Rehabilitation. And he also reviews grants for the Michael J. Fox Foundation and National Parkinson Foundation. At UF, he created the course entitled Movement Disorders, which is now the foundation course for a training grant from the NIH for training doctoral students in movement disorders. So today, Dr. Vaillancourt will be speaking to us on the use of automated imaging to differentiate forms of Parkinsonism. Welcome, Dr. Vaillancourt.
Thank you very much. It's really an honor to be here. And I'm going to talk for, I don't know, I have like 30 or 35 slides. And if I go on and anybody wants to ask a question, I just want to say, please ask a question as we go. If you have it, I certainly will stop. So what I'm going to do today, I'm going to talk to you about artificial intelligence, but I'm going to talk to you about it in the context of neuroimaging and Parkinsonism. And so I'm not going to go into the weeds or to the details of artificial intelligence, but I want to show you how it can be useful in the research that we have ongoing. So this is one of the first, and I think it is the first video on record of a patient with Parkinson's disease. And in it, you can see many of the behaviors that help a physician diagnose a patient today. You see a stooped posture, you see tremors in the person, you see what looks like to be a rigid person, so some rigidity going on, clear tremors in both upper and lower limbs. And many of these features are used in the diagnosis still today. So when a neurologist sees a patient, they will do a neurological exam, which will include looking at the way the patient moves and behaves. And many of these features are still used today to diagnose the disease. So I would like to talk to you about a few key numbers that kind of set the stage for some of the work that we have ongoing. The first of which is the number 0. If you think about what is called a disease-modifying medication, a disease-modifying medication is a medication that does not necessarily treat symptoms of a disease, but will reduce the progression and neurodegenerative qualities of a disease. And in the area of Parkinson's disease, there are 0 medications that are FDA approved to slow down the disease process. If you contrast this with another disease, which is also prevalent, and that's multiple sclerosis, there are at least 14 medications approved by the FDA to slow down the progression of multiple sclerosis. So you can see 2 different neurodegenerative diseases, one of which has many disease-modifying therapies, and the other is Parkinson's disease, which has none. And one of the reasons for this is because early on in the area of multiple sclerosis, they were able to use magnetic resonance imaging to spot lesions in the brain, and they were able to quantify those lesions and use those lesions to then determine if a disease-modifying medication could slow down progression in MS. And only recently have we started to discover that certain types of magnetic resonance imaging might be useful in the area of Parkinson's disease. And that's what I'm going to talk to you a little bit about today. Another number that is important is that Parkinson's disease can be misdiagnosed early on. And in fact, when you compare Parkinson's disease diagnoses to patients who go to pathology after one passes away, only 58% of early stage Parkinson's disease patients are accurately diagnosed. Of the misdiagnoses that occur, at least half of them, roughly half, have either multiple system atrophy or another form of Parkinsonism, which is called progressive supernuclear palsy. So MSA or PSP or other forms of what people call Parkinsonisms, they're not Parkinson's disease. They have a different pathology. They have a different treatment. And they're quite frankly more aggressive. And so they're progress faster than classic Parkinson's disease. And so for a neurologist to distinguish between Parkinson's disease, multiple system atrophy, or progressive supernuclear palsy, it's a difficult diagnosis to make. And some of the tools that we're working on that leverage AI and also leverage different types of imaging are meant to facilitate this diagnosis in the future. So I'm going to talk to you about a few things. First, I want to talk to you about our lab developed the first MRI progression biomarker for Parkinson's disease. It led to the first clinical trial using imaging as the primary outcome variable. And I want to tell you a little bit about that. And the third thing I'll talk to you about is the using magnetic resonance imaging to differentiate forms of Parkinsonism. And then finally, I'll talk to you about a new grant that we're currently conducting, which will try to translate some of these findings for use in clinical trials, but also in clinics across the US. So what is a disease-modifying therapy? A disease-modifying therapy is a medication that would slow down the progression of a disease. So for instance, some of you may or may not take a statin. A statin would be considered a disease-modifying therapy because a statin is meant to lower one's risk of future heart disease. So there's a classic study that looked at what is a medication called rasagiline in Parkinson's disease. It's an inhibitor of dopamine or the breakdown of dopamine. And it basically looked at a clinical rating scale, which is called the UPDRS. This is a Unified Parkinson's Disease Rating Scale. And higher scores on this scale mean the patient is getting worse, and lower scores means the patient is getting better. And in this study, they followed two groups of patients. One was what is called a delayed start paradigm. And the second is an early start group. And as you can see, the delayed start group got worse over a period of 36 weeks. The early start group that got rasagiline got better over a period of time. And then they started to worsen up to 36 weeks. And so one could ask the question, well, is this a symptomatic effect of the drug or a disease-modifying effect of the drug? And at this moment, at 36 weeks, we don't know. We don't know if it's symptomatic or disease-modifying. And you can think of a symptomatic effect of a drug as taking a Tylenol. So if you take a Tylenol, it reduces your headache, but it doesn't really treat the underlying disease process. It basically just kind of reduces one's temperature. So at 36 weeks, there was a significant difference in this medication. And then when you look at 72 weeks, it also was significantly different. And the hypothesis here is that these two lines will stay parallel, and the group that didn't get rasagiline early, the delayed start group, will never catch up to the group that got rasagiline early. That's the hypothesis, that those lines will basically stay parallel to one another. And so at 1 milligram per day, this particular drug was looking quite good. However, in the study that was published in New England Journal of Medicine, the authors also studied 2 milligrams per day. That was significant at 36 weeks, but it was not significant at 72 weeks. And you can see these two lines converge over here at 272 weeks. And this leads the authors to conclude that it is not disease modifying, certainly not at 2 milligrams per day. The company asked the FDA to approve it as a disease modifying therapy at 1 milligram per day, but they were declined because the FDA was not convinced that it was a disease modifying therapy. And that's because the authors and other people suspect that while they're using a clinical rating scale, which is called the UPDRS, this looks at symptoms like the video I showed you earlier, And if the medication can basically reduce those symptoms in a matter of an hour, well, those symptoms maybe get better, but that doesn't mean that the actual disease process is getting better. And so just like taking a Tylenol may lower your fever, it doesn't necessarily alter the disease process. And so what one wants is a medication or some sort of therapy that slows the disease process down. And that's the ultimate goal. So in the Parkinson's disease, you have a part of the brain called the substantia nigra. It produces dopamine. And in that part of the brain, the patients with Parkinson's disease lose neurons, and the cells die over time in the substantia nigra, and they die in a particular specific area called the ventrolateral tier of the substantia nigra. And this part of the substantia nigra is also where you have Lewy bodies, which can be found, and you also have synuclein deposits within those Lewy bodies. And so what we're trying to do in some of our studies is measure changes in the substantia nigra so that we can provide a measure or an assay that can be used in drug development going forward that might be able to be useful for determining if a drug is or is not disease modifying. So early on, we published a study where we looked at an image of the brain, which is shown here on the left, and then we looked at another image, the ventral part of the substantia nigra. So this is like the bottom of the substantia nigra here in B. And if you blow it up down here in E, you can see different regions of the substantia nigra. And what we tended to find was that the middle and caudal, basically these two back regions of the substantia nigra, are where you see the significant changes in Parkinson's disease. In the anterior front part of the substantia nigra, we don't see changes in Parkinson's disease. And so we've since then replicated that finding a number of times since 2009. And my student, Trina Mitchell, and I published this review in Brain, a commentary in Brain. And basically in the substantia nigra, it's like real estate. It is location, location, location. So when you are looking in the substantia nigra, it has to be in a specific part because early on, the specific part of the substantia nigra is affected. We think as the disease process goes on, other parts of the substantia nigra will also become affected, but early on, it's this back part of the substantia nigra, this middle and caudal part, which become affected. Now we're using a measure called free water diffusion MRI. So this is a technique that does not involve a contrast agent. It can be performed on 3 Tesla MRIs, which are readily available throughout the United States, mostly at major medical centers. There are many in Gainesville, for example, that you would be able to access. And if this is a voxel right here, what this technique is doing is it's looking at the diffusion of water molecules within tissue or the constraints on that diffusion process. And so if you assume that these little circles are cells and there's diffusion going on within the cells, then the blue is basically the extracellular compartment. And what the technique is doing is it's measuring the size of that extracellular compartment. And as a patient gets a neurodegenerative disease, the hypothesis is that that size of that compartment is going to grow. So the size of the diffusion going on in blue will increase. And so we're measuring the size of that diffusion compartment. And so I had a former postdoc at Atrophy who was able to study patients with Parkinson's disease over time. And as you can see here in the substantia nigra, this is a picture of the midbrain here on top. This is a patient at baseline. And you can see in blue is high free water, and in yellow and white is low free water. So you see these 2 different blue dots. Those are increases in free water in the substantia nigra. You can see the same patient 1 year later is shown here in the bottom. And you can see that free water in the substantia nigra is worsening and it's growing. And so what that suggests is that the free water content in the substantia nigra is progressing in that patient. And then we basically followed a group of controls and a group of patients with Parkinson's disease over a 1 year period of time. We found that the controls did not change, but the group of patients with Parkinson's disease did increase. Now, what that suggests is that this is not due to normal aging because the control group over that period of time did not change, but the PD group did. So it suggests that PD patients have an increase in their substantia nigra that can be measured. And so this was the first sort of MR progression marker that had been identified at that time. We've since then validated it in another study, which I'll show you in just a minute. And we used a cohort from the Michael J. Fox Foundation. There's a big international study going on that's supported by the Michael J. Fox Foundation called the Parkinson's Progressive Marker Initiative. In this study, we were able to get data from 103 PD and 49 controls, baseline in 1 year, and this is across 10 different MRI sites. And we were able to access another cohort across 4 years of only PD patients across 8 sites. So this isn't data that we acquired in Gainesville. This is a data that's being acquired at different sites across the world. We then asked the question, do we replicate what Mr. Ofori found? And this is Roxana's study. And what Roxana found was that indeed we do replicate that effect in another cohort. And basically in yellow is the control group and blue is the PD group. On the y-axis here is the 1-year change in free water in the substantia nigra. And what this says is the control group did not change over that 1-year period of time, but the PD group did increase, similarly to the way we saw it before. If then we are able to measure that group of PD patients that changed over 4 years, we can see that the substantia nigra keeps going up. The free water in the substantia nigra keeps going up year after year after year. Now, in each of these analyses, I mentioned that they were across sites. And across sites is really important because anytime you want to license a medication, you're going to have to measure it across sites because the definition of a phase 3 clinical trial is that it has to be performed across more than 2 sites. So the fact that in this study, we saw similar observations across the sites in the studies in A and the studies in B here are very important because it suggests that we're able to measure these effects across these sites accurately. And because of this, it might be useful in a future clinical trial, which would certainly have to be run across the sites. In this study, another thing that we found, which is important, is we looked at what is called the Yar Scale. The Yar Scale is a scale, it's a 5-point scale. And on it, 1 means you have symptoms on one side of the body as a patient. 2 is you have symptoms on both sides of the body. 3 is you have some postural problems. 4 is you basically are using a cane to walk. And 5 would be you're in a wheelchair. And so the numbers really mean something in this scale. And what we found was when we looked at the change in free water over 1 year, which is on the y-axis, we found that those patients that got better on the scale had low free water, which is -1. Those patients that had no change over 4 years had relatively low free water, which is in red. But the patients that got worse on that scale, which is in blue, had a massive increase in free water over that 1 year period of time. So this short-term 1-year change in free water is predictive of a longer-term clinical outcome of relevance in patients with Parkinson's disease. And this is important because it suggests that a future effect of a particular biomarker is relevant. So just like a statin may lower cholesterol, well, you know, if you lower cholesterol over a 3-month period of time, it doesn't mean that the patient looks better. They're not more handsome or prettier. They don't lose weight. They don't get stronger. But what you're doing by lowering cholesterol is you're reducing the risk of heart disease in the future. And so what we think is possible is if you're able to have a medication lower free water over a 1-year period of time, then you may be able to lower one's risk of progressing in the future because you're basically sort of staving off neurodegeneration of dopaminergic cells. So we recently tested this idea in the measure of the medication rasagiline. We wanted to go back to the study that was done in New England Journal of Medicine early on and study that same medication and see if we could detect a disease-modifying effect at 1 milligram per day from that particular medication. So this was the first clinical trial run where imaging was the primary outcome variable in Parkinson's disease. This was all run out of the University of Florida by our group. We also had clinical colleagues, Dr. Oken and Dr. Shukla. And so basically a patient was referred to the study. They were then told to go and do a baseline testing. So they did imaging and then some cognitive tests and motor tests. And then we would look at quality control analyses on all that data. And then they were basically assigned to an intervention. And this was done randomly based upon a statistician, Dr. Sam Wu, who basically told the UF pharmacy to put the patients into group 1, which would be an inhibitor of rasagiline at 1 milligram per day, or they would go into a placebo group where they took another pill that looked like the pill for rasagiline. They then took that pill, the rasagiline or the MAO inhibitor, the rasagiline pill or the placebo pill for 1 day, every day for 365 days. They then returned back to us for a 1-year follow-up testing, which is the same as baseline. And then we basically did the analyses. And what we found was This paper is just coming out of publication. We found that 1 milligram of rasagiline does not have a disease-modifying quality in early Parkinson's disease. So we found no evidence, which is in contrast to the study in New England Journal of Medicine. And I think that that suggests that rasagiline was having a symptomatic effect in that early study. It has no evidence for a disease-modifying effect. We also found that free water does still increase over 1 year in the PD patients. So this study replicated our prior studies that free water is increasing. And we also found that baseline free water in the substantia nigra is predicting clinical progression in PD, similar to what we found before. So the biomarker effects that we've observed before were all replicated, and we found that there are no disease-modifying effects of rasagiline. Okay, so does anybody have any questions so far?
Yeah, Dr. Vaillancourt, I may have missed this, but did you say these patients were newly diagnosed before they started the?
They were within the first 5 years of diagnosis. They weren't, so they weren't within a year. They were within the first 5 years of diagnosis.
Okay, thank you.
I think on average, they were about 3 to 4 years been diagnosed. So we're now using MRI to differentiate forms of Parkinsonism. So I mentioned at the very beginning that we're interested in differentiating Parkinson's disease from multiple system atrophy or progressive supernuclear palsy. And so, if you look at patients who've had Parkinson's disease or had a Parkinson's disease diagnosis, all of these patients have had a Parkinson's disease diagnosis, but any one of them could have a different form of Parkinsonism, and they might not know it because it takes a little while for a physician to sort of recognize that a different type of diagnosis might be occurring. And sometimes the misdiagnosis can occur. So even though you might think a patient has Parkinson's disease, later on, you might learn that the patient does not. And so we've been using imaging or diffusion imaging to not only look in the substantia nigra, we're looking at many parts of the brain. And we did this where you look at the free water difference, and this is showing you different parts of the brain. I'm not going to go through all of these parts of the brain, but basically these ones on the left with these 2 stars here are the substantia nigra. And in PD patients compared to controls, you see no other stars, which basically indicates all these other parts of the brain were sort of clean or healthy early on. In MSA though, in multiple system atrophy, you can see many different stars, suggesting that all of these regions are significantly different from controls. In PSP, you see stars in every region that I'm showing you here. And what this suggests is that these patients with MSA and the patients with PSP have a far different sort of brain fingerprint than the patients with Parkinson's disease. And so what we're trying to do is leverage that understanding and utilize a big data approach and an AI machine learning approach to then utilize a lot of data to see and find patterns in the data so that we can differentiate patients with Parkinson's disease from patients with MSA, from patients with PSP. So we started doing this several years ago, and we accrued a data set of over 1,000 subjects, participants from different scanners, and this is all across the world. Data was donated. We have 17 different MRI scanners in this data set, and we have 8 different international sites. We had in the study 278 controls, 511 PD, 84 MSA, and 129 PSP. This paper was published in Lancet Digital Health in 2019. And the importance here is, the real uniqueness here is the 17 different MRI scanners. It's not trivial to combine data across MRI scanners. And we did nothing to match the type of acquisition across scanners. So the MRI manufacturers, they don't want to talk to each other because they compete with each other. They want to make money. And so they don't talk to each other. And so we are basically including data from different MRI scanners and different MRI manufacturers, which allows us to predict diagnosis across them. And that's I think the real strength of this study. So this was done by Derek Archer. And what we did first was we developed parts of the brain. So we have a very standardized set of regions in the brain that we can use and analyze. And so this is basically a region of interest template of the basal ganglia, the midbrain, the thalamus, the cortex, and the cerebellum. We also have tracks, the white matter tracks that connect the cortex to the spinal cord. We also have transcallosal tracks that connect the 2 hemispheres of the brain together. We have tracks connecting the cerebellum to other parts of the brain as well. And then we also have tracks connecting within the basal ganglia as well. And so we use all of these regions and tracks, and we quantify diffusion measures, particularly free water and free water corrected fractional isotropy in these specific parts of the brain. And this is all done through an automated pipeline. So we just kind of hit the computer and say go, and it processes all the data one by one. And what we did in this study, so this is kind of the machine learning AI part. We did what is called a training and test set. So in this machine learning, it's really important because these algorithms are so powerful. You always want to have a test set. So we basically took 20% of our total subjects randomly, and we set them aside. So we did not look at them at all. We set them aside. And then we took 80% of the data as a training set. And in that 80% of the data, we did what is called five-fold cross-validation. We basically broke that 80% of the data into a 20-80 split. So 20% is here, 80% is here. Now that's only of the original 80%. And then we ran it again where we changed the 20%, we ran it again, changed the 20%, ran it again, etc. And what this did was we were able to train the algorithm and then validate the algorithm. And so it's trained on the green initially and validated on the blue each time. And then we took that algorithm, and after we trained and validated, we then went back to the original test set, which is in yellow, to ask the question, does it translate to a completely independent set of data? And so what I'm going to show you is the outcome of that specific analysis. And what we did was we ran a few different models. So we asked the question of a model for Parkinson's disease versus atypical Parkinsonism. So basically Parkinson's disease versus a diagnosis of MSA or PSP, which is a difficult diagnosis to make for a physician. And then we made the comparison of MSA versus PSP. And then finally, we looked at different combinations of diffusion imaging plus a clinical rating scale, diffusion imaging alone, or the clinical rating scale alone. And we compared these different models. So in the graphs, I just want to orient you. On the top left here is what is called true positive rate. So, and this is called false positive rate. So what you want in this sort of a graph is you want the lines here to go up to the top and come over. That's the goal of what's called a receiver operator characteristics curve. And so when you see a lot of area under this curve here, that's a good thing because it suggests that you're able to separate patients into specific categories. So in this case, we're looking at PD versus atypical. This is our training and validation cohort. And as you can see, the area under the curve, which is basically the area under these different curves, is relatively high in the diffusion imaging plus the rating scale. And it's also high in the diffusion imaging alone, but it's lower in the clinical rating scale alone. So the clinical rating scale doesn't do as good as the diffusion imaging. And then you look at the test cohort below. This is that 20% test cohort that we did not include in the training and validation. You can see that the model still is working very well on the actual test cohort. This is just some of the parts of the brain that were impacted into the model. And I'm not going to go into those in detail, but the key finding here is that the model is functioning really well in separating Parkinson's disease from atypical Parkinsonism. So the next thing we did was we asked the question, well, how about comparisons of multiple system atrophy to progressive supernuclear palsy? And what we found was that, again, the training validation cohort had high area under the curves here for whenever the diffusion imaging is used, but whenever the rating scale alone is used, it was lower. In the test cohort, we also found a very similar finding. The area under the curve is slightly lower in the test cohort than the training cohort, but it's still very strong. So the test cohort is still has an area under the curve over 0.9, which is still very strong. And again, the diffusion imaging is doing well compared to the rating scale alone. It's important to point out that the sort of fingerprint that we find, which is really the parts of the brain that are affected, are really parts of the brain that have been known for some time to be impacted at neuropathology. So after an individual has passed and a pathologist looks at the brain of a person with these diagnoses, they will identify that certain parts of the brain are impacted. And our algorithms, while a person is alive, is finding similar parts of the brain that are impacted. And that's important because it basically says that where we're looking in the brain and the algorithms are basically finding are consistent with where the pathology is thought to occur. And that sort of gives us more confidence in the outcome of these algorithms, that indeed they're actually finding something of relevance. So we also looked at a group of 5 cases that actually went to pathology. And the question was, does our algorithm match a pathological diagnosis? So as you can see here, a clinical diagnosis is on the left and the pathological diagnosis is here in the middle. In model 1, where it's PD versus atypical, our algorithm got it right in 5 out of 5 cases. In model 2, our algorithm also matched the pathology in 5 out of 5 cases. However, if you look at case D, you will notice that the clinical diagnosis was MSA, the pathological diagnosis was PSP, and if you look at our algorithm, we correctly identified it as PSP. So even though the clinical diagnosis was wrong, our algorithm predicted it to be correctly in terms of the pathological diagnosis. So this is certainly not enough data to make strong conclusions on whether the algorithm matches onto pathology, but it is certainly good evidence so far that we're on the right track. And we certainly need to test this in more cases in the future. But having said that, the current data is promising. Okay, so does anybody have any questions? So now we're at a point where we've kind of done a lot of work, and now we're trying to figure out, okay, what do we want to do next? And this is a nice graph because it shows a specific biomarker pipeline. You might discover a biomarker, you might then replicate the biomarker, you might validate it in validation studies, and then ultimately, though, you want to translate it. And to translate it, if you think about a biomarker, well, you want to translate it to clinical practice or into the community or into clinical trials somehow. And so the translation is in many ways the difficult part, because you have to take what you find in a laboratory in a very controlled setting and put it out in a much more noisy setting. And so what we're doing now is we are building a sort of database web infrastructure so that the algorithms that we've developed can be accessible to the outside world is the goal. And we're testing the algorithms in a new study, which is across many different sites. And so this has led to a new grant, which is called a U01 grant, which is funded by the National Institutes of Health. And we're currently exploring in that grant a translational aspect of the studies that we've done so far. So we have 21 sites in the study. All of the studies were chosen by a steering committee involved, and they're all part of what is called the Parkinson study group. So all these sites have expertise in Parkinson's disease, and they have good MRI facilities available. And so all these sites are mostly in the United States. So 19 are in the United States and 2 are in Canada. And we're currently working with the sites. They're all getting their IRBs set up, and most actually have their IRBs set up now. I think it's roughly in the order of about 15 or so have IRBs set up at this point. They all have their MRI protocols set up, and we're getting close to being ready to collect data at across the sites. And so the goal in this study is going to be to test the algorithms across clinically diagnosed patients across these sites to see if the algorithms are identifying the correct diagnosis consistent with what we've observed already. This is our team. So myself is here. Michael Oken is a good colleague, worked with for many years, wonderful neurologist. And Angelos Barmpoutis is a computer scientist, and he's also working quite extensively in this. And I'll show you the key part that he's developed so far, which is really the front-end website and database infrastructure for the project. Marissa Schauder is our study coordinator, and she's meant to liaise with all of the sites and communicate some of the key features with the sites, and that's currently ongoing. Samuel Wu is our statistician, who's helped us in designing some of the statistical analyses. Rogu Feng is a machine learning expert here at University of Florida and is helping us refine some of the machine learning algorithms. Stefan Prokop is a neuropathologist, and so if a patient were to pass in the study, he would perform the neuropathology for the study. And then Wei Wang is our image processing person, and so she's basically in charge of performing much of the image processing for the cohorts. And finally, Todd Parrish is at Northwestern University, but he's meant to set up the imaging sequences across the sites. And so he's responsible for making sure that the sites are collecting the right data and that they have the right sequence set up. So this is one of my last slides, but I wanted to play this video for you. So this video is going to basically show you where we're at in terms of the website development. So the central idea here is we have a piece of software which hooks into servers, and the servers are effectively meant to perform image processing and perform the machine learning analysis so that we can determine specific diagnoses. And so this is the front end of the infrastructure, and I'll just give you a sense of what that looks like. So you're going to hear a student, this is an undergraduate student at the University of Florida, explaining this device, and much of the programming is being conducted right now by undergraduate students at UF.
The main purpose of the AIDP website is to collect data needed for our study using nationally approved security standards and protocols. Here you can see the landing page of the AIDP website. Once their account has been approved, selected users from the contributing sites will be authorized to access the website and complete a registration form. Once their registration is approved, users can log into the website using a dual authentication process. Users will be sent a single-use dual authentication code that will allow access into their accounts on the AIDP website. In the main page, the users can see a list of the data they have contributed so far, organized by subject, or contribute data for a new subject by clicking on the New Subject button. You can click on a specific subject to open the data uploading forms. The data of each subject are organized into Visit 1 and Visit 2. There are 3 types of data that need to be uploaded for each subject: imaging data in DICOM format, clinical session videos that will be recorded and uploaded from the iPads, and clinical scale forms. To upload the imaging data, drag and drop a folder with the data in DICOM format. The data will be automatically de-identified on your browser by removing all the sensitive information from the header of the images. The de-identified version will be uploaded and securely stored in our server. To upload the video from the clinical session, click on the button and select Browse. Then, select the corresponding video from your media gallery. The clinical scale forms can be accessed by clicking on the list on the bottom of the page. Use the prompts to complete the required fields in each form. Your inputs are automatically saved to our secure cloud server. In free text responses, you may be prompted to correct your entries. The questionnaires are interactive and may reveal more questions based on your inputs. On the top of the form, you can track your progress. As you can see, we have completed this form. You can close the form at any time using the button at the end of the form. The progress status of each questionnaire is also shown on the list of the forms. You can go back to the list of subjects by clicking on the Home button. You can log out at any time by clicking on the Logout button. More information can be found in the Manual of Operations. The main purpose.
So one of the key things that was mentioned there was the de-identification. So when the images are transferred across the internet, they're actually de-identified before they cross to the internet, which is really critical. And it makes the transfer of data much easier, because when a person goes and has an MRI done clinically, the file itself, the image file, is going to have certain identifiers in it. They might have your name, they might have certain features. And so what we do is we look in those headers and we strip out all that information before it crosses the internet. It's actually done on the browser of the software browser before it actually comes across the internet. So it's a very safe way to transfer data, which is really important because a lot of hospitals are not set up to transfer data safely because they want to keep this information in the headers because they need it for internal purposes. So what we do is we strip it out first before transferring it. So that's all that I've prepared for today because I thought we might have some conversations about some of what I talked about. And I want to say thank you very much for your attention and hope to answer any questions that you might have.
Well, thank you very much, Dr. Vaillancourt. Very, very interesting. I do see that we have, let me see. I see we have one question in chat, and I always have a few questions. So Shirley, question from Shirley Bloodworth is, do many PD patients take dopamine, and how does this medication work? And are your study patients taking any medications?
It's a very good question. So I would say the large majority of patients with Parkinson's disease would be taking some form of dopamine replacement therapy. So they're going to take a medication called Sinemat, which is basically meant to increase the production of dopamine. They might take a dopamine agonist, which might increase the chances that the amount of dopamine they have currently is going to work effectively. So that's basically trying to enhance the dopamine that's available. Or they're going to take what is called an MALB inhibitor, which is the type of medication we studied, which is called rasagiline, which is basically blocking the breakdown of dopamine that's already there. And so all these medications are basically trying to increase circulating levels of dopamine in these key basal ganglia regions so that patients can move better and function better. So how many patients typically take medications? I would say most PD patients are going to take some form of a dopaminergic medication. In our studies, most patients are going to be on some medication already and would be unlikely, I think, that they would not be on a medication. The study that I talked about from Michael J. Fox Foundation is a unique study because it is looking at what's called de novo patients. So a de novo patient is a patient has never taken a Parkinson's medication. But those patients are somewhat rare. So in the United States, for example, about 50,000 newly diagnosed patients every year. And so, some centers see a lot of de novo patients and some centers don't see as many de novo patients, for example.
Okay, and that's actually a good segue to my question. So when you say de novo patients, so I was struck by one of your very early comments that over half of PD patients are misdiagnosed in the early stages. And so when you get a patient that you consider de novo, they've potentially had this disease for maybe several years. I'm thinking in particular of actually a friend of mine who was misdiagnosed for many, many years because of her symptoms were a little atypical, but some smart neurologist eventually figured out that her flank pain was actually a somewhat rare presentation and did correctly diagnose her. But so what do you do with those particular people? Do you disclude them from studies, or are they considered included? And are you seeing them as outliers of any sort?
It's a very good question. So in like the New U1 grant, the way we're doing it is about 13 out of the 15 patients that we accept per site, so about 15 patients per site, we expect to have a probable diagnosis, which means really the physician is very confident in the diagnosis. And we accept 2 of the 15 patients to have what is called a possible diagnosis. Now, these are still all clinically diagnosed patients. So even though it's probable, it does mean that it's not final and it could still change. But having said that, the physician is much more confident in that diagnosis. So our thinking on this is that if we develop a procedure that works where we're confident in patients where the diagnosis is more accurate, then we can test it on earlier diagnosed patients. If we're testing it on earlier diagnosed patients now, it's kind of like the input into these algorithms is going to get real noisy, I think. And so, we wouldn't know if the algorithm is working that well because, the input that we're putting into it is not known that well. So we're hoping to look at patients where the diagnosis is a little bit more probable, and then ascertain if the algorithm can find that out as well.
Okay.
And-
See, I don't see any other hands. So I have so another question would be, so when you talk about machine learning, what specific machines are learning? So are you working with, say, Hypergator on campus, or what is being used to collate and crunch all of this data?
So machine learning is like, some of the people on the call, if you were previously in some form of academic research, you might have done statistics, and you can do a t-test. And if you do a t-test, you're looking at a distribution of data between, the same measure in two different distributions of subjects, or you're looking at a regression analysis. And sometimes you might do a multiple regression analysis where you have multiple variables predicting one variable. Well, machine learning is really a machine, like a computer, learning characteristics of a data set. That's all it really is. And there's different types of machine learning algorithms. So some are, simple, some are more complicated, but they're all trying to learn patterns in data. And I would say the real uniqueness of a machine learning approach is it can take in many different variables. So it can take in all, many different regions of the brain that we feed it. So our classic statistical approaches might be looking at 2 regions of the brain or 5 regions of the brain, but we can feed it, 60 to 100 regions of the brain. We could even feed it thousands of regions of the brain. And by doing so, we're able to look for patterns that we as scientists might not be able to see. And so the machine learning algorithms are able to sort of detect this. And this is, I think, a wonderful thing. It's also something you have to be very careful with, because these machine learning algorithms are always going to find patterns. The real question is, do those patterns present themselves again? And can you consistently detect those patterns? And if you can, then you're going to have something that people might be able to use in the future. So, like Google or some of these other websites that we might go to, they are basically using advanced machine learning patterns to identify our behaviors and sort of give us what they think we want. And they're usually probably quite right in doing so. And so they are taking a lot of data, taking in features, and presenting to us what they think that we want. And so it's very similar to what we're doing. We're basically taking in lots of data from the brain and trying to predict a clinical diagnosis.
Okay, great. Thank you very much. I don't see any other hands up or chat. So I would like to thank you for joining us today, and very interesting lecture. And I hope we'll be seeing more on your work in the future. I'm assuming that your funding is for a considerable period of time to study this. So I think we're looking forward to being able to use computers to help us differentiate these Parkinson's diagnoses a little bit better. So thank you very much again.
I want to thank you all very much, and I appreciate you staying in there with me and asking excellent questions. Thank you.
All right, and everyone, I'll see you next week. We're going to be moving into a little bit different realm in AI. We're going to be looking at autonomous weapons technologies and who's involved with oversight. So stay tuned, and hopefully we'll see you all next week. Thank you, everyone.